Okay, it's 9 or 8 a.m. And we can continue. So today's goal, the main goal, will be to introduce this induced electric field. What is that? We will naturally come to that point. But before we start introducing this electric field, we need to look at the examples about Faraday's law. Pretty much at this point, we spent enough time practicing Faraday's law. At this point, we should feel like more or less experts. Now let's look at a few examples where Faraday's law is applied. Right? Very cool examples. Actually, it's plenty of applications. Okay, so you remember Faraday's law, right? So if you have some conducting loop which is exposed to the magnetic field, if flux produced by that magnetic field changes in time, then EMF is produced, and as a result, current will be flowing clockwise or counterclockwise, depends on what happens to the magnetic flux, right? And examples. The first one: how does an electric guitar work? It's purely based its work is based on Faraday's law. Okay, so here's a photograph, right? You see strings, and you see below the strings there are small cylinders. Under each string there are small cylinders. Let's just look closer at one of those cylinders, sort of like a zoom in. And here's the diagram of what you will see. So here's the string, right? And here's the coil. Basically, coil, it's a solenoid, right? Solenoid. And inside of the solenoid, you see this blue object, permanent magnet. North pole, south pole, right? So permanent magnet. And that permanent magnet is stationary. It doesn't move relative to this coil, relative to the coil. This magnet is stationary. Then above that, of course, there is a string. And the string must be made out of magnetized material. Of course, we never talked about magnetized materials, but in simple words, it's a material. If you expose it to the just a second. Okay, somebody muted himself. Okay, so if you expose that material to external magnetic field, then that material starts behaving like a magnet. So it becomes a magnet. Right? So in this case, this string is made out of magnetized material, and since it is exposed to this permanent magnet, to the magnetic field created by this permanent magnet, the string becomes a magnet. You see, north and south poles of this string. So now this string is a small magnet. Okay, and now let's assume that you plug this string. So first you displace the string to the farthest point, right? And then you release it, right? And so now the string, basically this magnet, starts moving closer to the loop. Since the string closer to the loop moves closer to the loop, what happens to the magnetic field created by this magnet, by the magnet of the string? What happens to the magnetic field through that coil? It increases because the magnet gets closer and closer to the coil, right? So again, I'm just trying to analyze the flux. 3 parameters, BA theta. Theta, we can assume it's almost constant. Area of the loop doesn't change, but magnetic field, as the string moves closer, magnetic field gets stronger and stronger and stronger. So as a result, magnetic flux increases. So of course this loop will wake up immediately, right, and starts reacting. In which way? Of course it rebels because flux increases, right? This loop, the coil, multi-loop system, right? This coil will respond and it starts driving current in a proper direction. Of course we can find out the direction, but let's assume for now, for example, clockwise direction, right? So magnet move closer, this string moves closer and closer and closer, and the coil produces current in a clockwise direction. Then once the string comes to the closest point, of course the string will stop for a moment, right, at the closest point. And of course, at that moment, current will be 0 for a moment. And then the string, of course, starts moving in the opposite direction, moving farther away from the coil. So now magnet through the coil becomes weaker and weaker and weaker. Flux becomes smaller. So now the loop again will respond to that, but now response of the loop will be opposite. Now the loop will be supportive, and it will drive current in the opposite direction. So if in the first part of the motion, current was in the clockwise direction, now current will be in the opposite direction, counterclockwise, right? So the string moves farther and farther away, current in a counterclockwise direction. Again, string reaches the maximum, the farthest point, again, current will disappear for a moment, and again, and then again, the next cycle. Clockwise direction of the current, counterclockwise direction, clockwise, counterclockwise, right? So basically what we are doing, right? We're converting with this system mechanical oscillations of the string to electrical oscillations of the current, right? And then of course this signal, of course it will be weak signal, right? Can be coupled out, can be amplified, filtered, right? You can do whatever you feel like doing, and then it can be sent to, I don't know, speakers or recording system, whatever, right? But of course you can ask me, so how come, but what about this permanent magnet which is inside of the solenoid, inside of this coil? Yeah, it also creates magnetic field, right? Of course, it also creates magnetic flux through this coil, but that flux is constant. It doesn't change in time. You remember Faraday's law, EMF equals minus d phi over dt, rate of change of the magnetic flux. So flux must change in order to produce the induced current. In this case, this blue permanent magnet, flux produced by the blue permanent magnet, doesn't change in time. As a result, it doesn't produce anything in this coil. But this magnet, since it moves up and down, flux changes, and it produces current in the coil, right? So that's how guitar works, right? As a result, mechanical oscillations of the string gets transformed into electrical oscillations of the current. Cool, right? So direct applications of Faraday's law. Now, next one, very similar. Microphone. Hold it. I need to press on the slide. Okay. Microphone. So you see, we have a box over microphone, right? And then again, there is a coil. You see this orangey line. So coil. Right? Again, it's all about coil. Right? And so there is a coil which can be moved back and forth, right? And that coil is attached basically to this membrane, diaphragm, right? And then inside of the coil, there is a permanent magnet. In this case, this permanent magnet is stationary. This permanent magnet, you see red and blue. It's a north and south pole of the permanent magnet. So it is attached to the box of the microphone. In this case, permanent magnet stays at the same place, but the coil, it's a light coil, moves up, back and forth. So now acoustic waves comes, right? And of course, this membrane starts moving, starts oscillating or vibrating, right? So it moves that way and then back and forth. So membrane moves. And of course, this coil will be moved with that membrane. So when membrane pushes the coil closer to the permanent magnet, so that permanent magnet, magnetic field created by the permanent magnet through the coil becomes stronger because the coil moves closer to the permanent magnet, right? So flux changes, flux increases, and of course the loop will respond to that. Flux increases, the loop starts behaving like a rebel and starts driving current in the proper direction. Let's say clockwise, for example. So when the coil moves that way, clockwise direction. Then on the next cycle, of course, this membrane will pull the coil away from the permanent magnet. So in that case, magnetic field through the coil becomes weaker, flux is dying, the system supports, and the loop starts driving current in the opposite direction, counterclockwise direction. So and so on. So now next cycle again, clockwise direction, counterclockwise direction, clockwise, counterclockwise, right? And that, of course, small current can be coupled out to some amplifier, maybe some filters, right? And then you can do with that signal whatever you feel like doing, right? So what happens in this process? A couple of transformations. First, information from the acoustic waves gets transformed into mechanical vibrations of this membrane, of this diaphragm, right? And then those mechanical oscillations get transformed into oscillations of the induced current, right? So couple of transformations, all right? And of course, frequency of these acoustic waves will be transformed to the frequency of course, of current will be exactly the same as the frequency of the acoustic waves, right? And the amplitude, of course, will be proportional, right? So pretty much all the information will be preserved, right? Okay, so that's how microphone works, right? Just typical microphone, right? So next example, maybe less cool, but very very practical. All right. So generation of the current. This principle, of course, is used in all power stations where current is generated. Okay, so the simplest diagram. So we have two permanent magnets, north pole of this magnet and south pole of the second magnet. And of course, between them, so you can position them closer to each other. So between them, there is a uniform magnetic field. You see those blue lines, magnetic field lines. And then if you position in this magnetic field a loop, you see in this case a rectangular loop, and of course it must be properly connected so that we can couple the current out of this loop. Right, it can be easily achieved mechanically, right? Okay, and so now let's assume that you start spinning this loop. What happens to the flux through this loop? Again, three parameters, B, A, and the angle. Magnetic field through the loop is constant, right? Uniform magnetic field, it's constant, it doesn't, we're not changing it, right? Then area of the loop also stays the same. We're not distorting the shape of the loop, so area stays the same. But angle changes, right? So what happens to the angle? So, so magnetic field is that way, right? So let's start with this point. So the loop, okay, I have a circular loop, right? Circular loop. So let's assume that a loop first is, okay, positioned like this vertically. So the area vector that way. So now first angle is 0 degrees. Again, angle, you remember theta between the magnetic field, which is that way, and the area vector. The initial moment of time, let's assume area vector also that way. So right now the angle is 0. Then you start spinning the loop, so now angle is 30 degrees, 45 degrees, then 90 degrees, then 110 degrees, 120, 180, then 270 degrees, and then 345, and then, I don't know, 500 degrees, and so on. As you keep spinning the loop, angle keeps increasing. Angle increasing, flux changes, current is produced. In this loop, current is produced in this loop. But let's look at the direction of the current. You remember, if flux through the loop, for example, increases, current will be in one direction. If flux decreases, current will be in the opposite direction. Let's look at what happens to the fluxes, right? So let's now start with this position of the loop, horizontal position, right? So can you tell me what will be the value of the magnetic flux through this loop at this moment of time? Magnetic field lines parallel to the surface. So as a result, you remember physical meaning of the magnetic flux. It's a number of magnetic field lines crossing a surface. In this case, if magnetic field lines are parallel, so they cannot cross the surface, so the flux is 0. And now let's start turning, right? Spinning it. So right now flux is 0. And if I start spinning, of course, now flux starts appearing. And flux is growing. Flux is growing as I keep spinning, right? And it will keep growing up to this position. when the loop is perpendicular to the magnetic field lines, right? So now the flux is maximum. So over this period of time, current will be, let's say, for example, clockwise direction. Now, after this moment, loop starts turning this way, and of course flux starts getting smaller and smaller and smaller and smaller. So it means flux is dying, so the loop will start driving current in the opposite direction, counterclockwise. So before it was clockwise, now counterclockwise, because now flux is dying. And now after this position, now again flux will be 0. Now again, if you start spinning, continue spinning, now again flux increases, current will be clockwise up to this point, and then again flux starts decreasing, counterclockwise, and so on. You see, we're generating AC current, clockwise, counterclockwise, clockwise, counterclockwise. AC current it will be generated, right? Okay, and of course you will see something like this. Of course, this is EMF plotted versus time, right? But of course, if you divide it by the resistance of this loop, you will get current. What a big deal, right? So that's EMF. Okay, now, so that's how we can create a current, right, or EMF. How can we increase efficiency of this system? Can be more productive, get more, right? Let's get kind of greedy. Let's get more current. So what can be done in order to increase the efficiency of the system? What if we can use, instead of one loop, what if we spin at the same time several loops? For example, one loop right now, okay, let me position like this, right? So let's say if one loop is, okay, probably like this, right? At this angle, the second loop will be at this angle, and the third loop will be at that angle. What if we arrange 3 loops in this way again? So for example, like this first one, the second will be like that, and the third will be like that. And start spinning them at the same time. We will get 3 currents. 3 currents shifted by 120 degrees. Of course, you need to arrange them properly, right? So you'll get 3 identical currents, but shifted by 120 degrees. It means what? For example, here we have only one EMF, right? But if we arrange the system like I just described, the second EMF will be shifted by a certain period of time, right? And for example, it will start from here, right? And again, it will be the same sinusoidal function. And then the third will be, maybe we'll start over here somewhere. It will be next sinusoidal function. So we'll have 3 exactly the same sinusoidal functions shifted shifted in time. So 3-phase current. 3-phase current, right? And yeah, of course, it just increases efficiency, but also at the same time, current we use quite often to run motors, right? And if you use only one phase current, the motion is not going to be smooth. It's not going to be good on electrical motors, right? So the motion is not going to be, yeah, as I said, not going to be smooth. But if you drive the electrical motor with 3 phases, then motion will be very, very smooth, right? Guys from EE department, I'm sure that at some point you will learn what's the difference if you drive the motor with the 1-phase current or 3 phases, right? So that's what is usually used in power stations. Of course, power stations generate 3 phases, 3-phase current. Okay. First section of the typical hydroelectric power station, right? So we have a dam, right? High level of water, right? In order to create pressure, right? And then water is being guided to the turbine, right? Through this like a pipe, right? Penstoke, right? And that water spins this turbine, right? And then through the shaft, this rotation sort of moved or and the turbine spins over here coils, right, in the generator, right? So there are all those, as we just discussed, a bunch of coils over here, right? And as a result, in this generator, 3-phase current is produced, and then that current can be, of course, sent to the consumers, right? And of course, this is the photograph of one of the generators. And of course, usually there are many of them, right? Again, in order to increase efficiency of the hydroelectric power station, right? Okay, so that's these are examples which I wanted to discuss, right? It should be enough. It should be enough. So at this point, we can say, no, it's too early. I want to say enough about Faraday's law, but it's not true. Right. So we will still talk about Faraday's law, but you will see from which point of view. Okay, so now finally we can move to the main goal of today's class. Induced electric field. You remember the title slide, right? Induced electric field. So now it's time to move into that, right? Yeah, these are the sections. So what's the goal? So here's the form of the Faraday's law which we've been using, right? EMF equals to minus rate of change of the magnetic flux. There is nothing wrong with this law. It's a universal law, fundamental law, which can be applied at any point of the universe, at any moment of time, and it must work. So far, no one has found any examples where it would fail to work, right? Nothing wrong with this law, but this form of Faraday's law is usually is used by what? By technicians, engineers, applied physicists, but hardcore physicists, theoreticians, for example, they barely use Faraday's law in this form, right? Why? Because EMF, it's a very, very practical quantity, right? But again, mainly used by, as I said, technicians, engineers, and applied physicists, right? But not a hardcore physicist. They usually use what? They usually use fundamental quantities. What do I mean by fundamental quantities? Electric field and magnetic field. All right? Also, this is it's one of the equations in a set of Maxwell's equations, right? So basically, this equation forms like a foundation of electromagnetism. And foundation must be written in terms of, again, fundamental quantities. It must be written in terms of electric and magnetic field. Again, EMF, nothing wrong with EMF, with the potential difference. But again, it's a very practical quantity. And it doesn't consider it as fundamental quantity, right? Again, from the point of view of applications, EMF is much better, right? Much more useful to use than electric field. But again, from the point of view of physics, it's better to write this fundamental law in terms of electric field and magnetic field. That's the main goal of today's class. We need to rewrite it in the most general form. Again, I'm emphasizing we're not introducing a new law. We're just rewriting Faraday's law in the most general form. And again, where is the magnetic field? Not a big deal. Magnetic field is inside of the magnetic flux. It's a B dot A. So pretty much we know where the magnetic field is. But electric field, we need to introduce, of course, electric field on this left-hand side of the equation. So we just need to rewrite EMF in terms of electric field. That's the main goal of today's class, right? Okay, so now, so how should we introduce this? As usual, right? What do we usually do in education, right? So usually we start from sort of a comfort zone where we are comfortable, with the stuff which we know, and move into a zone which is less comfortable for us, right? From the comfort zone to a less comfortable zone, right? And we work there until we'll start feeling comfortable, right? So now the same. Let's do the same here. Let's start with the example with which we are very familiar at this point. We should be very comfortable and move into a less comfortable zone. So we're going to make 2 additional steps. The first step will be kind of obvious. The second step will be far from being obvious. It will be even, I would say, counterintuitive. So at that point, you will have to trust me. But the first step is quite obvious. So let's start. Again, as I said, from the place where we quite comfortable. So let's assume that we have a uniform magnetic field, B external. Let's assume that we have some conducting loop, right? And of course, we can analyze. We're going to get induced current, and what's the direction of the induced current. We've done this example many times. So at this point, we should be very comfortable. Okay, so let's assume that magnetic field, this B external, is increasing. You see, we have increasing uniform magnetic field. Right? So let's get direction of the current, induced current. Since flux is changing, of course, current will be produced. So let's just get the direction. As usual, Lenz's rule, 3 parameters. Area of the loop stays the same, angle constant, magnetic field changes. So as a result, actually not just changes, magnetic field increases. Magnetic field, okay, let's say increasing. Magnetic field is increasing. Of course, magnetic flux also increasing. So of course, the response of the loop is well known. So the loop rebels. And it will drive the current in such a direction so that the induced magnetic field will be in the opposite direction relative to the direction of the external magnetic field. So within the loop, as a result, I can draw a bunch of dots representing induced magnetic field. And now, right-hand rule, dots, it means out of the board, so I have to position my hand like this. In order to get this direction towards us. And my thumb gives me, as a result, correct direction, which is counterclockwise direction. Right. As I said, it's at this point you should be quite comfortable doing all these steps, right? So as a result, induced current in a counterclockwise direction. So that's initial point. And now we need to make 2 additional steps. First question, if there is a current, there must be something which creates this current. Current usually consequence of something. What is that? Usually response of the students immediately because of the potential difference. Yes, that's true. That's usually, as I said, immediate response of the students. But that's what we have, potential difference in our current form of the Faraday's law, EMF, potential difference, right? But we want to move away from the potential difference. We want to move deeper into the description of this process. So what else must be sort of applied in order to get current in the conductor? Electric field. Electric field must be there, because what is effectively a current? Current, it's a drift of charges. Charges drift if you push them. In our case, what do we use to push these charges? Electric force. Electric force can appear only if there is an electric field, right? If this is, for example, positive charge, electric field that way, of course, electric force will be also that way, and charge will start drifting. We create current. So there are 2, we can say there are sort of, in order to produce electric field, we can say there must be potential difference or there must be an electric field. This over here, there must be an electric field. This electric field is called induced electric field. Induced electric field. It's a first step, which is kind of obvious, right? I don't have, after my speech, you should be convinced, right? So there must be electric field. And these electric field lines, these induced electric field lines, form circles. Why? Because you see, charges move around the circle, right? So at any point, for example, if at this point, charge must experience which force? Force along the tangential, right? So electric field, so force tangential, and of course electric field will be also in a tangential direction at any point. This point, that point, right? So at any point, electric field must be tangent to this loop. So electric field lines form electric field lines form circles. All right. So I can open up. Wait. So at this point, electric field is tangent. At this point, tangent. That point, tangent, tangent, tangent. Right. So electric field lines form circles. So it's a first step. That's why I put here Roman symbol 1. Right. There must be induced electric field. And I emphasize, although I'm kind of lazy person, right? But you see, every time I keep pronouncing induced electric field, induced electric field. Before this, right, like at the beginning of the semester, every time I just used to say electric field, but now I keep adding induced electric field. And of course, it's a very important because, yeah, all of these fields, they're electric, but there are some differences. Some properties of this electric field are different relative to the electric field which we discussed, analyzed at the beginning of the semester. On the next slide, I will sort of juxtapose these two fields. This is an induced electric field. There are some different properties, although both of these fields are electric fields. All right. Okay, now the second step, as I promised to you, we're going to make 2 steps. And the second one is not intuitive at all. Okay, so we have a loop, we have a current, there is an electric field, right? Electric field lines are circles. Now, let's imagine this situation. What if I just grab this conducting loop and move it away from the magnetic field? What would be different? If I just grab this conducting loop and move it away from the system, would we have a current? Would we have the current, induced current? Of course not. Current would disappear because if there is no conducting loop, then where current can flow? Current can flow if there is a conductor, or in this case, conducting loop. So if I remove the conducting loop, current would definitely disappear. But what about the electric field, this induced electric field? This is the major point. Surprise, surprise, this induced electric field will be still there. Pretty much this whole space is filled with this induced electric field. And it doesn't matter if there is a conducting loop over here or not. This is not obvious. So you have to trust, right? So basically that's how God programmed the nature, right? So basically, changing in time here magnetic field produces this induced electric field. And induced electric field will be here, it doesn't matter if you have a conducting loop in the system or not. But of course, current can be only if there is a conducting loop, right? You understand? Current, it's a drift of charges. You must have charges, right? If you don't have charges in the system, then there's nothing to drift. Okay, so this step, as I promised to you, it's not obvious, right? So you just need to trust me, right? In this case, we can say that conducting loop, it's almost like a probe system. If somebody doesn't believe you, so that there is a electric field over here, you can just grab the conducting loop, put it here, right? And you can say, you see, there is a current flowing through the loop. Current can flow only if there is an electric field. So you see the current, so there must be an electric field. Or you can grab, you remember that small positive probe charge, position it, and of course the probe charge will give you a direction of the electric field. Position it at several spots in order to convince somebody that there is an electric field, right? But again, in order to produce this electric field, the loop is not needed, right? Okay, so we sort of introduced this induced electric field on a conceptual level, on the level of blah, blah, blah. But we still haven't reached the goal, because you remember what is our goal? To rewrite Faraday's law, to get rid of that EMF from the left-hand side of the Faraday's law. We haven't reached that, so now let's do that. So you need to understand, what are we trying to replace? We're trying to replace EMF, which is effectively electric potential, okay, potential difference. And we want to replace it with the electric field. You remember from the past, do we have any bridges, or did we introduce any bridges which connected electric field and the electric potential. You remember chapter 26? Immediately after the first midterm exam, where we learn how to move from the electric field to the electric potential and how to move back from the electric potential to the electric field. So we just need to recall that and use one of those formulas. And we're going to use that 26.3. So you remember, that's how we moved from the electric field to the potential difference between between this initial and the final point. So the potential difference, usually we would pick some path, and potential difference at the final point minus potential difference, minus electric potential. Okay, electric potential at the final point minus the electric potential at the initial point equals to the negative integral along the path between these 2 points. So we need to apply this formula for our case. And again, you remember, we are trying to replace EMF. EMF produced where? In the closed loop. So it means that if I, for example, start counting potential differences, EMF, if I start from this point, I have to move around the closed loop, around the whole loop, and I need to get back to exactly the same point in order to get our EMF, because you remember EMF is produced in the closed loop. So now, in order to apply this formula, what can you say about our final point and initial point? It must be the same point, this one, right? So this is our initial point, and then when you complete the loop, you'll come back to exactly the same point. That will be our final point, right? So in order to get our EMF out of this delta V, we need to integrate over the whole loop, right? And as a result, on this right-hand side of the equation, we're going to see integral over the closed loop. So we're going to see a small circle at the center of this integral. You remember the meaning of that circle in the middle of the integral? Integration over something which is closed. In this case, it's a closed loop, right? So instead of delta V, as a result, we have EMF, right? You see EMF. And that integral over the closed loop, E dot ds. Don't ask me about that minus, right? Forget about it. Usually books, I looked through several books, they usually try to move over that minus without discussing it. So EMF equals to integral over the closed loop of E dot ds. ds is the element of that of the loop. Okay, so that's what we can get from this formula, applying this formula for our particular case. But of course, according to the Faraday's law, EMF equals to negative rate of change of the magnetic flux minus d phi over dt. So now we can combine this with that integral, and we are getting the final, the most general form of the Faraday's law. Left-hand side, it's that integral over the closed loop, E dot ds, and the right-hand side, negative rate of change of the magnetic flux. So again, this is our EMF, and that is our right-hand side of our old form of the Faraday's law. So this is the most general form of the Faraday's law. You can open any book in physics, right, at the page about Maxwell's equations in an integral form, written in an integral form, and you will see usually this is equation number 3. You will never see a physics book with the whole set of Maxwell's equations where EMF is used. No, every time it will be written in this way, in terms of electric field and magnetic field inside of this magnetic flux, right? In terms of fundamental quantities. Again, EMF, it's a very useful, ridiculously useful quantity, but it's more for people who work with applications, right? For physicists, usually it's an electric field and magnetic field. Right? Okay, so now let's look at the structure of this law. On the right-hand side, the rate of change of the magnetic flux. This magnetic flux, changing in time magnetic flux, is the source of what? Source of this induced electric field. So on the right-hand side, we have source, a source, And on the left hand side, inside of the integral, we have a field which is produced by that source. We had very similar structure when we introduced Gauss's law, for example. You remember, integral over the closed surface E dot dA equals to Q enclosed divided by epsilon naught. So again, Q enclosed, what is that? Sources, charges, sources which produced which produce electric field, which is shown on the left hand side of the equation. Charges on the right hand side produces electric field, which is shown on the left hand side of the equation. Then Ampere's law, exactly the same structure. You remember, integral over the closed loop B dot ds equals to mu naught times I enclosed. I enclosed currents are sources of the magnetic field, which is shown on the left hand side of the equation inside of the integral. And now Faraday's law has exactly the same structure. On the right hand side we have sources, rate of change of the magnetic flux, and on the left hand side we have electric field produced by these sources. All Maxwell's equations have exactly the same structure. On the right hand side we have sources, on the left hand side we have fields produced by those sources. And of course, all those fields all the time is shown inside of the integral. It's a very nice, elegant structure of all Maxwell's equations. Right? Okay, so now let's apply this Faraday's law for very, very special case in order to get to tremendous conclusion after getting some water. So let's apply that, assuming that, for example, we apply for a loop which is area of which is constant, and let's assume that our angle is 0 in order to take care of the right hand side of the equation, minus d phi over dt. Right? So what will be the flux in that case? Flux, it's a dot product, and it will be in our case, if area is constant and angle is 0, it will be equal b times a. And as a result, let's rewrite Faraday's law for this special situation. Again, left hand side will be exactly the same, integral of E dot ds, and instead of d phi over dt, now we'll have a db over dt. And you remember I told you just now, on the right hand side we have sources of fields shown on the left hand side. So what is the source? dB over dt, rate of change of what? Magnetic field. So this is the source, and it produces what? It produces electric field. Changing in time magnetic field produces electric field. This is something tremendous, really tremendous at this point, because you remember, basically we started this semester treating electric field, or electric world and magnetic world as two independent worlds, right? And you remember that Ørsted experiment which I discussed with you as a first example, where first case where people realized that there is a connection between these two worlds, between the world of electricity and the world of magnetism. And now we're realizing that electric field can be produced by the magnetic field. Probably for those people back then it was a mind-blowing sort of conclusion. Basically it means that these two worlds, electricity and magnetism, they're inseparable. They're so deeply connected that it's impossible to separate them. That's why it is called usually just electromagnetism. One field can be produced from the other one, right? Of course, changing in time magnetic field produces electric field. It's something really tremendous, something great. And that's why these guys keep jumping, and it will keep jumping until I move to the next slide, right? Okay, right. So, and that's what happened in the previous example, right? When we have basically uniform magnetic field, and if that magnetic field changes in time, electric field is produced, forming with electric field lines in the form of circles. Right? For example, if I have a solenoid, let's say solenoid, right? And let's assume that current through the solenoid is changing in time. Of course, what can you say about the magnetic field inside? It will be uniform, but changing in time, because current is changing in time. So changing in time magnetic field inside of the solenoid is going to produce induced electric field. Inside of the solenoid, we're going to have electric field lines in the form of circles. Again, whenever you see changing in time magnetic field, there must be induced electric field over there. That's how God programmed this world. We're just trying to model it, just trying to describe it, right? And that's what people observed, right? And that's how we model it, right? Okay, so now then you remember I told you about the two types of electric fields, right? And now let's just juxtapose their properties. Of course, I'm not going to ask on the exam about these properties, right, or compare properties of these two fields, but it's just for you, because at some point in high-level courses, of course, you will dive deeper, and so that you would be somewhat familiar with these ideas, right? Okay, so two fields. So first box, second box. This box will be about the old electric field. We can call it Coulomb electric field. And now the new electric field, the induced electric field, right? Okay, so now sources of the Coulomb electric field. Point charges, our electrons, protons, right? So produced by charges. And of course, Gauss's law describes that, right? You remember Gauss's law? On the right-hand side, we had the charges Q enclosed. And on the left-hand side, we have electric field. Coulomb electric field. So Coulomb, Gauss's law, of course, describes appearance of the Coulomb electric field. Then induced electric field is produced by what? Not by charges, but changing in time magnetic field. This you see, dB over dt. Changing in time magnetic field produces the induced electric field. So that's the source of the induced electric field, and sources of the Coulomb electric field, charges. Right. Second, about the electric field lines. You remember at the beginning of the semester, Coulomb electric field lines, they start on positive charges and end on negative charges. All the time Coulomb electric fields, they have beginnings and they have ends, right? Okay, you remember those pictures, right? Induced electric field, no beginnings, no ends. All the time they form closed loops. Of course, in our the nicest, the simplest situation, when we had uniform magnetic field, electric field lines formed circles. But of course, it doesn't have to be in general, right? So for complicated magnetic field changing in time, of course, induced electric field lines will have a complicated shape. But all the time, they must form closed loops. Right. Okay, so yeah, that's the example, basically our example, which we just discussed like 10 minutes ago. And the last part, again, it's probably for most of you it will be confusing, but I just want to state it, and in some higher level classes you will dive deeper into that. So you remember Kirchhoff rule, Kirchhoff loop rule. Whenever you have a closed loop, right, you remember in a circuit, and if you start moving from, for example, from this point, moving around, counting all the potential differences, you remember delta V's plus delta V1, delta V2 plus delta V3 plus delta V, and so on. Once you complete the loop, what we had at the very end? Zero. All right? The total potential difference, if you add up all the potential differences around the loop, at the end, when you finished adding up, you must get zero. That was the case with the Coulomb electric field. But now, and of course that field was a conservative field. But now for the induced case, if you integrate over a closed loop, E dot ds, that's our EMF, right? And now it's not zero. It's minus a rate of change of the magnetic flux. as a result, this induced electric field is not conservative. Again, I will never ask you on the exam anything about this, but I just wanted to expose you to that, right? Because again, all of, especially the last part, yeah, needs deeper explanations, right? But I just wanted to mention that these two fields are quite different. Okay, some properties are different, not quite different. Some properties are different. Okay, so and now, in order to conclude this class at this exciting moment, so I created a separate slide. So again, our Faraday's law, right? One of the fundamental laws, right? And now you see that these fields are so deeply connected. Field of magnetism, field of electricity, right? So electric field can be produced by magnetic field. So pretty much it's sort of like these fields are inseparable, right? So that's why I created this picture, right? So sort of like an eternal dance of electric and magnetic field, right? Especially it will be impressive when we get to optics and we start discussing electromagnetic wave. That's probably the most spectacular system, the most impressive system, at least from my point of view, right? But of course we will discuss that maybe in like 3 classes. But for now, at this point, at this exciting moment, let's finish this class. And if you have questions, you can ask. Otherwise, I will see you on Thursday.